Okay, here's classic thing. You've all handled a garden hose before. Um, the water coming out of here is going at a nice steady flow. If you close this end, if you make this end smaller, it's got kind of a Pascal type effect. Big pressure out here, small pressure here, but the water's going faster. So faster moving water has less pressure than slow moving water. Okay, that's why it's faster because it needs the energy from here to push it to go faster. Okay, and so this, it's all the same. All right. Again, you've got this much water because here's what's happening. You've got this much water, this mass of water here moving nice and slow through this big thick pipe, and then we've got to get this much water in the same amount of time. We got to get this water through this pipe, so it's got to go faster. In other words, this part pushes this part. Same amount here, but it made it go faster. Okay, because rho v, and so rho v equals AV times delta t. So the distance it had to travel. So it's got to speed up. All right. Because it's got the same amount of time. It's going to cover this distance in this amount of time. It's going to cover this distance and this distance in the same amount of time. So therefore, it's got to go faster. Okay. So your continuity equation is this part equals this part. Okay. So here's your continuity. So the density times the area, the cross-sectional area, times V1 is equal to the density times the cross-sectional times V2. That's your equation of continuity. Okay? And in an incompressible fluid, in other words, one that the density stays the same throughout, then you've got A1 V1 equals A2 V2, and the flow rate, the volume flow rate, Q, is equal to, why does that work? Because look, you've got meters squared times meters per second. So that's cubic per second. Cubic meters per second. So that's why that works. Okay, so a garden hose has an unobstructed opening with a cross-sectional area of 2.85 times 10 to the negative 4 meters per second. It fills a bucket with a volume of 8 times 10 to the negative 3 meters in 30 seconds. Hey, we've got a flow rate. Okay. Find the speed that the water leaves the hose through the unobstructed opening and through an obstructed node with half of as much area. This is kind of a tricky problem. Let's just do this on our own, and then I think we can call it quits on this. All right. And I mean, I could walk you through the slide, but let me show you it so that you get used to seeing what the equations look like written out. All right. So real quick, let me write down the thing. A1 is equal to 2.85 times 10 to the negative 4 meters squared. A2, the new opening, would be half that area, so that would be 2.85 divided by 2 times 10 to the negative 4 meters squared. Okay. Luckily, they didn't give us half the radius. So, I mean, they've already given us the area, so that's nice. We don't have to do the pi r squared hocus pocus. And then the Q is equal to, the flow rate is equal to 8.00 times 10 to the negative 3 meters cubed per 30 seconds. All right, so let me show you what I just did. There we go. So from that, I've got, here's the flow rate. All right. Here's flow rate. So we know so here's what we've got. We know that Q, from the unobstructed hose, this is how long it took. Q is equal to A1 times V1. Okay? So V1 is equal to Q over A1. right? So we can type those in. Uh-oh, I didn't have my calculator handy. Sorry. So you can watch me type this in here. So what are we going to do? Q is 8 second e to the negative 3 divided by 30. So that's equal to Q. That's my Q value. So Q is equal to 2.67 times 10 to the negative 4 meters cubed per second. Okay? Now, look what happens when I divide this by a meter squared, by an area. That cancels, that cancels, I wind up with a velocity. See how that works? So I'm going to take this, so I'm going to take 2.67 times 10 to the negative 4 meters cubed per second divided by 2.85 times 10 to the negative 4 meters squared. See how that works? That's pretty slick. Divided by 2.85 second e to the negative 4. That way. And it's 0.3935 meters per second. All right, so that's how fast that one fluid is flowing. Okay, now it goes into something that's half the area. So let's take that half the area, figure that what 2.85 divided by 2 is equal to 1.425. Okay, so here's what we've got. We've got A1 V1. We know what V1 is now, is equal to A2 V2 because it's the same water. We've got to figure out what V2 is. Hey, this actually works out pretty good because look, well, I didn't even need to do that division because I know that A1 V1 is equal to 1/2 A1 times V2 because it says it's got half the area. So I'll multiply both sides by 2. The half goes away here. Divide by A1. 2V1 is equal to V2. So just multiply V2 by 2. Hey, that worked out pretty nice. 0.935 times 2 is equal to 1.87 meters per second. Boy, I hope that's the right answer that they came up with. I didn't check the slide, so I want to make sure. Yep. Cool. Now we'll talk about Bernoulli's equation in the next episode.